Good morning, everybody. Let's go. Today we are going to finish this first part about finite element formulation, and we are going to finish talking about two more items. First of all, we are going to talk about solid elements, which is an extension of what we have been doing the last days. We're going to see some interesting things about these solid elements, not only the formulation, because it's just same or similar things. And then finally, we're going to finish the class talking about the convergence, which is something quite important when you are working with finite element modeling. Okay, so let's talk about solid elements. We've been talking about bar elements, one-dimensional elements, plane stress, and even axisymmetric problems, and now finish with this three-dimensional problem, these solid elements. And this formulation involves same ingredients as now. And here we have this Tonti diagram of the governing equations of the problem. It's the same Tonti diagram in the strong form. Remember that here we have the differential equations. So we have we look for a solution point by point in all the domain of the problem. So we involve the displacements as our primary variable, the strains, which are the first derivative of these displacements, the stresses, which are related with the strains using a constitutive law. So in fact, these stresses involves a first derivative of the displacements as well, and they are constrained by these prescribed displacements, which involves this primary variable, the body forces and the prescribed tractions, which involves this stress domain. So this is our unknowns, so this is our data. The one in yellow are the yellow squares are the known and the unknowns, and the red ones are the problem data. So this is the problem we are trying to solve, the same scheme we've been following until this class. This is the weak form. Remember that our strong form is transformed using this total potential energy principle. So we are solving a minimization problem for the equilibrium equations and the prescribed boundary conditions in forces. So our problem is a weak form using this integral of the energy. So this is what we call the weak form of the problem, and this is something important we're going to talk a bit later when we talk about convergence. So in the case of solid elements, fan modeling, there are some important things to say, because really the world is three-dimensional problem. So usually we have to solve a three-dimensional problem, and we want to model all the details in our structure. So these solid elements allow us to make a much more realistic simulation, considering the boundary conditions. They are applied in a realistic way. The loads are applied in a realistic way. The geometry is able to take into account all the details. So in fact, we are trying to model three-dimensional problems. This is our objective. The point is that this three-dimensional simulation has got a quite expensive price to pay, because usually our meshing work is quite much more difficult. The computational cost is quite higher if you want to solve a three-dimensional problem. Even the post-processing phase could be much more complex, because the results we are going to obtain are quite much more difficult to interpret. So three-dimensional problem is not the big thing when we want to solve, depending on the complexity of the geometry in our problem. For example, usually in three-dimensional problems, we try to avoid details like this. Try to avoid details, small details, which does not affect to our physical problem. A good modulation is the one who is able to capture the physical phenomena which is taking place. So this is what we are trying, where we try to point, the physical phenomena. So try to avoid all the details that make our results much more complex to find and to interpret. So usually we can find, for example, concentration of stresses in the boundaries, or our problem has got a too high computational cost, so we can't afford this time of computation. So usually we try to simplify our three-dimensional problem to a b-dimensional problem if we are able to capture the physical phenomena which is taking place. In fact, the conclusion is that if you make a three-dimensional simulation, it's because you've got a very good reason to do it. Maybe the person who is demanding your simulation wants to see a three-dimensional simulation because he wants to see all the details. It's much more spectacular to present a three-dimensional geometry with all the results. But this does not mean that your simulation is better. Okay? Sometimes the geometry allows you to make a three-dimensional simulation without too much changes. So your problem allows you to do it, but you must think always about which is the physical point you want to simulate and try to simplify. And usually a bidimensional approximation to your problem can give you quite a lot of information to, at the end, make a three-dimensional simulation to get the good results. Okay, so usually our bidimensional problem conditions our final three-dimensional simulation. Okay, this is your choice. This is your choice, and this is your work to model the problem in a proper way, taking into account the accuracy of the results and the computational cost you are assuming. Okay. If we talk about solid elements, we have three standard solid elements as a reference, usually employed in this simulation. Same way that we have triangles and quadrilaterals in the plane stress or in the plane problem. In three-dimensional, we have tetrahedron and hexahedron, usually the most useful solid elements. I like hexahedron. I prefer hexahedron for three-dimensional simulation. Tetrahedron has got the same capabilities and the same problems as triangle. It's very easy to get a mesh with tetrahedron, but for structural analysis, the results are not very good. So we use tetrahedron above all to teach in the finite element formulation. Although if you want to get a good result with tetrahedron mesh, you must use a lot of tetrahedron elements to get a good accuracy in the simulation. So I usually prefer for a three-dimensional simulation the hexahedron, we call it brick, this hexahedra element. We have this pentahedron element, which is with a triangular base. It's not very common, but sometimes it's useful for very special cases. For example, imagine that you want to make a structured mesh. This is a typical example. This is a dam, and you want to make a structured mesh of your domain, and you sooner or later will have to make this, and you will find these kind of elements here, these triangular based elements, solid elements. So to adapt a structured mesh to non-rectangular domain, non-square domain, we use these sort of Toblerone elements, we call it, called pentahedron elements, weights. And there is another typical use of this pentahedron, is that if you want to make a three-dimensional mesh of with the extrusion of a plane problem, so imagine we have this plane problem with triangles, and we want to create a three-dimensional problem for this plane problem using an extrusion tool of this domain. So these triangular elements becomes this pentahedron, this wedge element, solid element. So in some specific situations, this could be a quite interesting, quite useful solid element, the one in the middle. but usually we work with tetrahedron and most of all with hexahedron. This is the three reference solid elements, and they are represented here with the nodes in the corners. So we have 4 nodes, 6 nodes, and 8 nodes for these 3 reference solid elements. They are not only formulated with the nodes in the corners, so we can create solid elements with the nodes in the midpoints of the edges. So here in the upper part, you have the representation of a quadratic tetrahedron, hexahedron, and a quadratic pentahedron, the 3 reference solid elements, and we have 2, let's say, non-standard elements, non-standard solid elements, which is these 2 elements here in the lower part. The one in the left is the pyramid. So sometimes we can use this solid element if the geometry reclaims this kind of meshing. And this element in the left, in the right, we call it brick because it's the mix of a brick element, of an hexahedron element, and a wedge. This one in the middle. So this one and this one, if you make a mix, you can find this brick element. It's not very usual in the field element modulation, but it's the possibility to, if the geometry reclaims this kind of elements, to use this brick element shown here. Here we have represented the nodes in the midpoints of the edges, but it's not necessary that these nodes must be placed in the midpoint, so we can place the nodes everywhere depending on the kind of element we want to use and the information we want to get. These solid elements, all of them, the reference ones and the non-standard ones, can be formulated using this isoparametric method. So we have a geometry definition, again, depending on the number of nodes, where the geometry, in this case, we have 3 Cartesian coordinates, x, y, and z. So we need, for n nodes, n shape functions, 1 per node, in the way that these 3 coordinates, Cartesian coordinates, are expressed using this interpolation, again, using these nodal values. That's the coordinates, nodal values for the geometry, that's the coordinates for every node. So we have 4 nodes, we have 8 nodes, we have 6 nodes for the 3 reference element, and this consistency condition, which says that the shape functions must sum 1 every point. So this is the same formulation we've been using the last days, so with the plane elements and the one-dimensional elements. Again, our primary variable is the displacement function, so we must interpolate this primary variable, this displacement function, and for it, in the isoparametric formulation, we use the same shape functions as we use in the geometry. So we have now 3 degrees of freedom per node. We are in a 3-dimensional problem, so we have 3 components for the displacement, and if we consider n nodes, we have 3 times n components for the matrix, for the nodal values of the displacement. We are going to use to interpolate all the displacement function using this same n interpolating shape functions, same as the ones we used in the geometry. So our interpolation for the displacement function will be this, expressed for the 3 Cartesian coordinates and the 3 displacement components, x, y, and z, in the solid problem. Here we have the vector of the degrees of freedom. So we have 3 degrees of freedom per node, so 3 times n unknowns for the displacement. The strains now have got 6 components, all of them, the ones in the strain tensor. Same thing with the stresses. Remember, in the plane stress and plane strain we have 3 components. In the axisymmetric problem we have 4 components. Now we have all of them 6 components for stress and strains. And the kinematic condition for the strain displacement equations and the strain displacement matrix we are going to find comes for these partial derivatives with respect to the Cartesian coordinates. of this displacement function. So this displacement function is calculated like this. This is the continuum problem. This is the interpolation of the displacement, and we apply the derivatives of these shape functions with respect to these Cartesian coordinates using these nodal values. So this strain function is expressed like this B strain displacement matrix times these nodal values of the displacement. We have the constitutive equations. These constitutive equations relate these strain and stresses vectors. Remember that this in fact is a tensor, is a matrix, so it's a 3 by 3 order matrix, but we express these strain and stresses components using these 6 component vectors. So we have a 6 by 6 order elastic matrix, constitutive matrix, relating these two magnitudes, and using all the formulation coming from this total potential energy principle, this minimization problem, and lead us to the expression for a element stiffness matrix. So for any element with n nodes, we have this expression coming from this minimization problem, this variational formulation, which says that this stiffness matrix is the integral of the B strain displacement matrix transpose times the elastic matrix times this same B matrix all over the volume. Now it's a volume in the solid element, and we can calculate this stiffness matrix using a numerical integration. So now we have Gauss integration rules as usual. We must decide this number of Gauss integration points. So this stiffness matrix can be calculated using this summation, considering these weights. This B strain displacement matrix, remember that these are expressed in the usually in the natural coordinates, and this Jacobian, which involves the changing variable between these Cartesian coordinates and the natural coordinates. Okay, this is the Jacobian matrix. In fact, this is the determinant of the Jacobian matrix involving this numerical integration. Now we're going to say something about this integration. Usually, sometimes there is this possibility of calculating this B strain displacement matrix using this form here, and calculate this value here inside the integral. This value here inside the integral, we're going to call it Q. We can calculate this value using a closed form. This is due to the fact that in our solid problem we have a lot of zeros in the matrix. So in the numerical integration, most of the calculations would be zero because of these zeros here. This is the B strain displacement matrix, and again, so these zeros lead us to a lot of non-necessary calculations. So sometimes we express this term inside the integral in a closed form like that. So imagine we have operating this value of the B strain. This is the component of the B strain displacement matrix. This is the component of the elastic matrix. So we calculate B transpose times elastic matrix, and again this C matrix is the first product. The second product, that means this C matrix times B, is calculated in the closed form. So we find finally these expressions for this integrand, which is 3 by 3 stiffness matrix block, so as to avoid a lot of zero or null calculations, which it has a computational cost, but we are not interested in calculating that. So usually, sometimes in this three-dimensional problem, we express this integral in a closed form like that. Okay, and I think this is everything in the general formulation for the solid element. Now, in every case, we are going to assume this is necessary or not. And yeah.
Could you repeat the last part, because I don't understand why you say that we reduce cost.
So imagine we have this B matrix here with this 0, 0, 0, 0, okay, and this B transpose matrix with 0. So we are trying to calculate this term here inside the integral. If we do that, we're going to find lots of zeros, okay, in our integral here. Even in this elastic matrix, there are some zeros. So we're going to multiply, lots of these terms are 0. So if you make this multiplication of the matrix numerically, you are going to make lots of unnecessary calculations in the computer because you are calculating zeros. Okay? To avoid that, you can implement in your implementation work, you can implement this product directly using these expressions here. So with these expressions here, you don't multiply this matrix, and this matrix, and you directly write in your computer these expressions so as to avoid this multiplication. Take into account that this multiplication, you are going to make this summation operation, you are going to make this multiplication once and again. So you're multiplying lots of zeros. So to avoid this computational cost, usually we can express directly this multiplication, this product, in a closed form like that, so as to avoid these multiplication calculations, which are most of them unnecessary. Okay? Any more questions about this? Well, this is the general formulation. Now we are going to precise in each particular case. We are going to say some things about, for example, the linear tetrahedron. Remember the linear triangle, so we have now some formulation for the linear tetrahedron. We define this linear tetrahedron using these 4 nodes placed in the corner. So these 4 nodes with the coordinates, Cartesian coordinates, define our tetrahedral element. An important point is the numeration of these nodes. So there is a convention for this numeration, which are the distribution of the numbers, because we want to calculate this volume of this tetrahedra, and we want to guarantee that this is a positive quantity. So we want to assure that this volume is positive. We calculate this tetrahedra using this expression. This is 1/6 of the determinant of this matrix here. And to guarantee this positive number, we want to assure that the numeration is following a convention, which means that if you are placed here in this node, you choose one node, you look from this node to the opposite side, and looking from this, which will be the last node, this is the 4th node, the last one, you look at the opposite face, and you choose a counterclockwise direction of the numeration. So this is the numeration we want to, this is the numeration we must define, looking from this node 4 in the opposite side to guarantee this positiveness of the volume. This is a convention, just to work with the positive values of the volume. So once defined this numeration and once known the Cartesian coordinates, we define our natural coordinates. If we are talking about linear tetrahedron, we must make an extension of the triangle idea about the natural coordinates, or this, we call it triangular coordinates in the plane problem. So, but the idea is the same. So for every of these 4 nodes, we have a natural coordinate. We can call it G, 1, 2, 3, and 4, which has one value in this corresponding node. So for this G1 natural coordinate in node 1, we have one value, and we have a surface parallel to this opposite side, which is translating, and which has this decreasing value, the way that this value 1 becomes 0 in the opposite side. So G1 is 0 always in the opposite side. So we can interpret this natural coordinate as a translating surface from this corresponding node to the opposite side. Same idea we used in the linear triangle in plane stress problem. We can interpret this as a volume ratio. So if you place this point inside the tetrahedron and you join this point with these 3 nodes, 2, 3, and 4, you define a smaller tetrahedra which volumes over the total volume is calculated like this natural coordinate. So this natural coordinate is this volume ratio between the volume defined by the point and the total volume of the tetrahedra. Okay, so this natural coordinate has got these two interpretations in a tetrahedral volume. Okay, so now we got our natural coordinates, which means that for every function f, we can calculate an interpolation of this f function depending on these natural coordinates using these 4 natural coordinates and the values in the 4 nodes, in the 4 corner nodes. So this is our interpolation expression for a linear tetrahedron. We can express it in this way using Einstein notation. So if we choose as a f function the Cartesian coordinates, this Cartesian coordinates function, we can express the interpolation of this geometry using these 4 shape functions and these 4 nodal values for each of the 3 components of our 3 degrees of freedom per node. This is the consistency condition. Again, typical from isoparametric formulation, we can invert this relation between Cartesian and natural coordinates. So natural coordinates could be expressed from the Cartesian coordinates using this expression here. This is the total volume of the tetrahedra, and the displacement interpolation is again using these 4 natural coordinates, linear tetrahedron, and the 4 values for each component. So we have a linear interpolation of the displacement function. So this will be our isoparametric representation of all the relations between geometry and the primary variable E and the shape functions using these nodal values. These 3 rows are for the geometry, 3 rows for displacement and the consistency condition. And to calculate this strain displacement relation, which we saw in the general formulation before, now we have these 6 components for the strains, the 3 general components, and these distortions. Remember that this is the distortion divided by 2, but the tensor, the distortion is twice the tensor quantity. So this is distortion divided by 2. So we multiply by 2, we get the total distortion for these 3 components. These are the partial derivative operator, and we have this displacement vector considering these 3 components of the displacement. We have this interpolation using the shape function. So now this derivative operator times the displacement gets to the strain tensor matrix using this B strain displacement matrix relating the strains and the nodal values of the displacement, considering an expression like that. Remember that this for these natural coordinates, these partial derivatives are constant. So we have constant components of the V strain displacement matrix, and this was our displacement vector. Now we have 4 nodes, so we have 12 components, so 12 degrees of freedom in our tetrahedron, linear tetrahedron element we want to solve to get the solution of the problem. The stresses are got using these constitutive equations, considering this elastic matrix. In a general way, this elastic matrix is 6 by 6 order matrix. So we have 36 components relating these 6 stresses and 6 strains for the 3-dimensional problem. This is a known elastic matrix, known matrix for the elastic problem. So in general, the constitutive equation relates these strains, this strain and these stresses using this 6 by 6 order matrix. And finally, we got to the stiffness matrix using the same expression we saw before, integrating this term here, considering this B strain displacement and this elasticity matrix saw before. Taking into account that this B strain displacement matrix has got constant components, we can take out this matrix out of the integral, usually consider an homogeneous material, so this elastic matrix can come out of the integral, and usually for this linear tetrahedron we can calculate this elastic stiffness matrix like that, with this term, constant term, times the volume, because we are integrating over the volume of the tetrahedron, and this is the calculation of this stiffness matrix for a linear tetrahedron element. and taking into account the consistent nodal vector for body forces, in this case for body forces, the expression is this one, you know, again, involving this shape function stiffness matrix and these body forces. So we have no partial derivatives here. We have this stiffness shape function matrix, which involves these 4 natural coordinates. This is a way to represent this stiffness, this shape function matrix times the body force. Usually this body force has got 3 components, so we must integrate this this term over the volume. Now this matrix is not constant, so we can take out of the integral, but we must make it we must calculate the integral to get this consistent nodal vector for the body force. Remember that this consistent nodal vector is consistent because of the result of our minimization problem of the total potential energy. So everything goes more or less like we saw in the plane problem, but extended to the three-dimensional problem. Remember that with the linear triangle we had the same conclusions because we had a P strain displacement matrix with constant components. We took out the integral, and we calculate in a closed form this stiffness matrix as we did as we can do in the linear tetrahedron. And what we said in the quadratic triangle, we can say something similar to this quadratic tetrahedron. Now it's created using 10 nodes, 4 of them located in the corners and 6 of them located in the midpoints of the sides. This is a typical quadratic tetrahedron. Now this distribution of nodes allow us to consider a non-straight, curved configuration of this element, because we can interpolate the geometry using a parabolic function in every edge. So here these 3 nodes allow us to much more complex interpolation of the geometry. So we can use this quadratic tetrahedron when the geometry reclaims this kind of interpolation. But if we use this quadratic tetrahedron, the natural coordinates can be interpreted in the same way, considering this corresponding node. For every node we have a shape function. For this corresponding node 1, we have a shape function with 1 value and 0 in the opposite. So we can interpret this natural coordinate as a translating surface between this point and the opposite side, and this is accurate even with the curved sides. But the interpretation as a volume ratio, now it doesn't hold if the sides are not straight, because these volumes are not calculated in the same way with curved sides. So we keep this interpretation for this quadratic tetrahedron, considering this surface, even a curved surface, to define these natural coordinates. So again, we have an isoparametric representation, same as usual, 3 rows for the geometry, 3 rows for displacement and the consistency condition. Now the shape functions are a bit more complicated, but it follows the same idea as it was with the quadratic triangle. Remember that we must for any node we must get a 1 value and 0 in the other nodes. So we have 2 kinds of nodes in this quadratic tetrahedron. We have nodes in the corner and we have nodes in the midpoints. So imagine this node, for example, here, this node 1 must have a shape function that vanishes in all of the other nodes and has 1 value here. And remember that this node here has a natural coordinate which is 1 here and 0 in the opposite side. So the shape function involves this G1 coordinate, which means that these 3, 5, and 6 nodes vanishes. Now we must vanish these 3 midpoint nodes, and we do it with G1 less 1/2, because G1 natural coordinate from this node is 1/2 in these 3 nodes. So G1 times G1 less 1/2 vanishes the shape function in all of the nodes, non-corresponding nodes with respect to this one. So the corner node has got a shape function with this shape, G1 less 1/2, and then we have a normalization factor again because we want to get one value in this corresponding node, node 1. So we have a normalization factor which is 2. So finally our corner shape function, these 4 shape functions, has got this same shape involving the natural coordinate of the node 1, and the midpoint nodes, for example node 5, involves always the natural coordinates of the 2 nodes, adjacent nodes next, because G1 coordinate vanishes all the opposite side, G2 coordinate vanishes all this opposite side, so at the end we have only this node 5 which don't vanish it. So with this formulation here, with this line product method, we got that this node 5 got a 1 and got a 0 in the opposite sides in the other nodes. So again, this normalization factor assures us this 1 value in this node 5. So the midpoint, the 6 midpoint nodes has got these shape functions with this shape, which is the same as in the quadratic triangle we saw some days before. So we have these shape functions for these nodes for the quadratic tetrahedron, and again now it's not so easy to calculate this partial derivative, so we're not going to get a constant value, constant components matrix. So we usually use this numerical integration, and for this numerical integration we use Gauss integration rules like this one. So we have 1-point rule or 4-point rule to integrate this this quadratic tetrahedron, which means we must evaluate this function for every function in these 4 natural coordinates, and this numerical integration over this volume is calculated like that. Is the evaluation of the f function in these 4 natural coordinates, 1/4 all of them, or for 4-point rule we get this numerical integration evaluating this any function, this f function, general function, in this 4 combination of natural coordinates where alpha and beta are prescribed values, are known values, just to get an integration, numerical integration of this integral here. We got a degree 2 and degree 1 depending on the Gauss integration rule we are choosing, just to assure an exact integration of polynomial of degree 1, of degree 2, depending on what we are interested in getting. So our stiffness matrix now usually is evaluated using numerical integration. Now we are not able to take out this term out of the integral, so usually we use this numerical integration because the functions are too complicated to calculate. So B is the strain displacement matrix, and this B depends on the natural coordinates. So usually we evaluate this B in the integration points, same as this Jacobian, which is the determinant of the Jacobian matrix, which give us the relation between Cartesian and natural coordinates. So it's a bit much more complex this quadratic tetrahedron with respect to the linear tetrahedron. Usually we use I think linear tetrahedron is quite more used than this quadratic tetrahedron in finite element simulation, but we have the possibility of simulate a much more complex geometry using this geometric interpolation with quadratic shape functions. Okay. Backslide.
Yeah, there in this 4-point rule, I don't understand why independent of the values of the shape of the function, you substitute with these values of alpha and beta.
Because it's not independent. Okay. When you use a numerical integration rule, your integration points are prescribed. You don't choose which is your integration points, because the Gauss rule gives you where are your integration points. For example, here in the first one is T1, T4 are evaluated here in 1, 4, 1, 4, and 1, 4. So this is the 4 values for these 4 natural coordinates. So if you calculate your integral in this point, and this point is defined by these 4 values of these natural coordinates, if you make the integral in this point, in the Gauss integration point, you will get a degree 1 exact integration. Okay? So to understand that this 1/4 is not independent of the natural coordinates. Well, same thing when the Gauss integration rule has got 4-point rules. So you integrate in these 4 prescribed integration values, integration points. So you don't decide the natural coordinates in your integration. The point is that these alpha and beta are the combinations of the location of the points for these natural coordinates. So you've got 4 integration points. The first one has got 4 natural coordinates. First of these natural coordinates is 0.5854. The second, the third, and I'm talking about this one, okay? You're integrating in this point. This point is defined by 4 natural coordinates. Which ones? Instead of 1/4, 1/4, 1/4, 1/4, we have 0.58 alpha and 0.13, 0.13, 0.13. These are the 4 natural coordinates of your Gauss integration point. You've got another one, and another one, and another one. So you've got 4 integration points divided by these 4 natural coordinates depending on this alpha and beta. Same thing in the plane problem. We have a combination of weights and locations of the Gauss integration points. Okay, and you integrate, you substitute your natural coordinates with the coordinates of these Gauss integration points. Remember that when we were talking about one integration point in plane problem, with one integration point, your natural coordinate was 0. So you calculate your integral in this t equal to 0. You use 2, you've got 2 integration points, and these coordinates, this location, are prescribed. And in this plane problem, it was 1 divided by a square root of 3 and minus 1 divided by a square root of 3, so you don't decide. So the location of the Gauss integration points in Gauss integration rules are prescribed. Okay? The same with 1 point and same with 4 points. Okay? It's clear?
Yeah. And I have another doubt in regarding to this. Here you have to include also the Jacobian term of the transformation between the Cartesian coordinates and
Yeah.
this.
You will have to do it in your numerical integration of the stiffness matrix. Okay? This is a general presentation. This is not for a stiffness matrix. I mean, this is what you would find in a numerical integration book. So in a general case, for this integration of any function f with one integration point, you will get to this integral here with f evaluated in this integration point. And same thing with this. Now, we are going to say this f function is the term we have inside the integral. This term is expressed in Cartesian coordinates, but we want to, in natural coordinates, but we want to calculate in Cartesian coordinates, so we must change the variable. Now, this Jacobian matrix will appear afterwards, because this is a general presentation of the Gauss integration points, the Gauss integration weights, and the Gauss integration rules. Okay, so here we are not talking about changing the variable. Okay? Yeah.
How do we compute the Jacobian in natural coordinates?
The Jacobian.
Yeah,
The Jacobian.
Coordinates and we're working with this, so it's not clear for me. Like we won't get a square matrix.
No, we have an interpolation. Okay, so we have a. We have interpolation from the Cartesian coordinates to the natural coordinates. Okay, so now.
For instance, in the case of
I know.
work with t and
Yeah.
We have two coordinates and two
I-
x and y, for example.
Yeah, I think usually a three-dimensional case is a free independent coordinates space. I think these four natural coordinates are conditioned by a consistency condition, so in fact we have three. So the point is that we are going to work with three. So because, yeah, I don't know, this consistency condition here, we are using four because we are using four nodes, because the tetrahedron has got four faces. But these four natural coordinates are not here, but these four natural coordinates are related with this consistency condition. So in fact, we could work with three. Why we could work with three? Because in three-dimensional space, we have three independent coordinates. You can invent more if you want, okay? But in fact, you have three independent coordinates because you haven't got four. So one of them can be expressed in terms of the other one. So you got a relation between 3 and 3. So you always must have a square relation between your Cartesian coordinates and your natural coordinates.
Yes, another option between one of them or with just.
Well, you can express the other ones, the other three, so one of them instead of the other, in terms of the other three, and change the expressions when you have these four natural coordinates, this fourth natural coordinate. Because in fact, we don't have four independent coordinates. That's why it exists this consistency condition. Okay? Because our three-dimensional space is not a fourth-dimensional space. It's three-dimensional anyway, although you need four natural coordinates to describe your tetrahedron because you've got four faces. Okay? Over here. Any more thing? Any more detail? Yeah.
Just delete one, and we're left with three triangular coordinates. But can I express these four triangular axes in
In three axes?
In particular elements?
Well, in fact, we did it in the triangular element. Yeah? And we did it putting the axis using two of the edges, because the third one, in fact, was this third dependent component. So we could express these natural coordinates with three natural axes following three of the edges, as we did in the triangular case. I haven't got this presentation here, but triangular case was like that, and we said we have three natural coordinates. Well, it's not like that exactly, because we can express all these points in this triangular case using these two axes for the natural coordinates. What happened with this one? Well, in fact, this one is an edge which accomplishes this condition. So imagine the tetrahedron will be the same thing. So imagine our fourth point here with this third axis here. So this face will accomplish something like that. I don't know, delta equal to 1. So in fact, we haven't got four independent coordinates. We work with these four because it's easier for us. But in fact, we have three independent coordinates. And we can express all of this using these three axes, which is, I think, you wanted to ask. Okay? Whereas it's easier to work with these four natural coordinates because we have four faces, four nodes, and everything is expressed in a similar way, in an easy way. Okay? What more? Well, we are talking about this numerical integration, and well, finally, this is the evaluation of the stiffness matrix using this numerical integration. So as I said, B and J are evaluating these integration points, prescribed location integration points. Okay, and same with this consistent nodal vector. Now we have this shape function matrix expressed in natural coordinates, so we are not able to take out in the of the integral, so we calculate in the same way using this numerical quadrature. And this is the treatment we are describing for this linear and this quadratic tetrahedron. Hexahedron elements, which I think are quite more interesting than tetrahedral elements, so above all for bending problems. Bending problems are, this is quite better than the tetrahedron. I'm not going to show much more slides because everything is calculated in the same way. It's an extension of the quadrilateral elements, and even from this hexahedron element we can easily extract the solution and the formulation of these, of all of them, all of the hexahedron elements. This is the simplest one, considered but 8 nodes, and again this 8-node linear hexahedron has got his isoparametric representation using these 8 shape functions. Maybe the most interesting thing is that we must assure that this volume is positive, and to do it we have a convention to define this numeration of the nodes. So we choose one node, this one node, for example. This node is belonging to this face, and to this horizontal face, so 3 faces are related to this node 1. So we choose one of them, for example this horizontal node, this horizontal face. Now we place in the opposite face looking at this bottom face and describe a counterclockwise sense of the numeration. So if we are considering this node and this bottom face, we are here in this top face looking at the bottom. Our numeration must be 1, 2, 3, 4 with this counterclockwise. And when we have defined this numeration, we just extend these 4 nodes to the opposite side with 5, 6, 7, and 8, following the same counterclockwise, and identifying this 1 to this 5, 6, 7, and 8. In this way, we assure that the volume is calculated in a way that we always get a positive value for this volume of this solid element, which is something we need to guarantee the consistency of the formulation and to solve the problem. The shape functions are easily calculated, banishing the values of the functions in the opposite sides. I think it's much more easier than in the linear tetrahedron. So if we define a natural coordinates axis like that, remember that this, like in the quadrilateral elements, we define the natural coordinates between -1 and 1, considering the Gauss integration rules. So this face is g equal to 1, the opposite face is g equal to -1, this face is here is eta equal to -1 and eta equal to 1. So for every node, this one node, it's easy to banish the shape function in the opposite sides by using these binomial terms here. Same thing as we saw in the quadrilateral, so 1 minus g and 1 minus eta banishes this shape function in the corresponding opposite sides. Now in the 3D problem, it's just a question of adding this binomial term with this third coordinate, and this is the normalization factor, which from the 1/4 in the plane problem comes to 1/8 in this 3-dimensional problem, and all of these 8 shape functions are calculated in this way. So it's very easy using this line product method to get the shape functions of these 8 nodes for a linear hexahedron, as we have defined the last slide, in a very compact notation. We can express these shape functions using this point where g sub e, eta sub e, and mu sub e are these minus or positive and negative sign in these 8 shape functions. So once defined these functions, we can easily calculate the p-strain displacement matrix and the stiffness matrix and the consistent nodal vector in the same way. So we are going to extend in this formulation again. Just a couple of words about this hexahedron elements. This is the 20-node hexahedron element defined by these nodes. They are placed in the corners. 8 of them are placed in the corners. So it's 4 and 4 nodes in the opposite sides, and now we have 12 nodes placed in the midpoints of the faces. So we have 4 and 4 and 4 nodes placed in the midpoints of the face of these edges. So we have a 20-node hexahedron element, which has, think that in the linear hexahedron we have 24 degrees of freedom. Now we have 20 nodes with 3 degrees of freedom, any of them. So we have 60 degrees of freedom. This is quite a lot of degrees of freedom. This is something the computer must calculate. And we have one more hexahedron called 3-quadratic 27-node hexahedron, defined by this point, where we have nodes in the corners. So it's 4 plus 4 nodes in the corners. We have the same 12 nodes placed in the midpoints of the edges. And we have 6 more nodes placed in the center of the faces. So 6 faces with this point, this 23 point, this 26 point, this 25 point, this 22 point, are placed in the center of the faces to define that this 27-node hexahedron. That means that for 27-node hexahedron we have 81 degrees of freedom. We must solve for to get the displacement function in this element. So we're considering a quite high degree of number of degrees of freedom. So these are the typical 3 hexahedron used in the finite element simulation. I can say that this is quite expensive element, but quite good element for bending problems. 20-node hexahedron, 27-node hexahedron, they are usually used in a very precise, very accurate simulation, although they are very expensive. Okay? And
There's the current node, which is in the center, based on a row or physical row.
physical. Well, in fact, it's to complete our grid. You know, it's a grid we translate because we are talking about a Lagrangian element. You can define your element without this center node, just without this center node. But you will have to define your shape functions in a different way. If you're using a Lagrangian element, the definition of the functions is quite easy, quite mechanical. Okay? But nobody forbids you that you create an element without this central node. There are some simulations where this central node helps you or annoys you. So your experience must give you the answer about which is the element you are going to use. But usually we use this 27-node hexahedron because it works. Okay. So if you are able to create an element, you can place the nodes you want if you are able to guarantee the consistency conditions. The point is that maybe you create an element that it serves to nothing, or don't guarantee the completeness requirements, or don't get the convergence ratio you want. But you can create anything you want. For example, you can say, I don't want this node to be in the midpoint. I want this node to be 1/3, 1/4. Okay, you can do it. Just calculate your same function, and let's see what happens with your Jacobian, for example. Even you can change your Gauss integration rules. You can say, I don't like Gauss integration rules because I don't want to locate the integration points in these prescribed positions. You are going to define a different quadrature. You can do it. But then you are going to evaluate which is the degree of accuracy your results get with these different kind of elements. I know some people that dedicates time to create different elements and see if these properties of these new elements are good for this problem, for his particular problem. Okay. This is the standard finite element. This is the standard 27 node hexagon, but there are a lot of more, even people that wants to create a new element for this particular problem. Okay. Just a couple of words about the three-dimensional modeling, because as I said in the beginning of the class, you must be very clear if you want to make a three-dimensional simulation. You must have a very good reason, because take into account that we consider this is the constant strain triangle, the linear triangle, and the constant strain tetrahedra, the linear tetrahedra. If we compare, we have 6 degrees of freedom, 3 nodes, 2 degrees of freedom per node, that's 6 degrees of freedom, so our stiffness matrix has 6 by 6 order matrix. If we change to the three-dimensional problem, it's 12 by 12 order matrix. If we have a mesh, a plane mesh of 20 elements, just prescribing a size, defined size of element, we have this 20 times 20 times 2 degrees of freedom. This is the number of degrees of freedom, which means we have 800 degrees of freedom. If we get the same mesh in three-dimensional problem with the same size of element, we have 20 times 20 times 20 times 3 degrees of freedom per node, which means we must solve 24,000 degrees of freedom. This is something we must think about if we want to get to the three-dimensional simulation. So if we double the number of elements, we mean that we have 4 times degrees of freedom. If we do the same in three-dimensional problem, we're going to multiply by 8 our degrees of freedom. Just if we want to refine the mesh using a double, a half of the size of the element we are using. We must take into account that this bandwidth is quite higher with 3D and 2D. This is a storage problem. So maybe we are not interested in store all the matrix. So we must take into account that in 3D this bandwidth is quite higher, so we must use quite a lot of memory to store our stiffness matrix or our variable. So usually, this is something I recommend, I usually work in this way. We simulate b-dimensional problems as an approach to the three-dimensional ones, just to get the interesting conclusions, the properties, the general behavior and the physical problem in b-dimensional problems. It's possible, and usually you can take interesting conclusions from b-dimensional problems just to approach a general or a more precise, more accurate three-dimensional simulation. So we usually work in 2D just to know something about the problem and not to spend too much time calculating a three-dimensional problem. So we usually don't start using a three-dimensional problem, because it's much more expensive to calculate, to conceive, to get the mesh, and to interpret the results. Sometimes the three-dimensional problem gives you results difficult to interpret, difficult to understand. So it's much easier if you do it in a b-dimensional problem just to take conclusions. And one more comment. Considering the computational cost, imagine that we define this ratio between the computational cost we use in the assembly of the stiffness matrix and the solver with respect to the total computational cost in the CPU. If we define these two ratios, in the dimensional problem, these two ratios are similar. So the assembly of the matrix and the solver spends similar time, similar fraction of time in the solution of the problem. But if we come to 3D, this ratio is quite less, or this second ratio is quite higher than the first one. So the solver is going to employ the most of the total computational cost with respect to the assembly of the stiffness matrix. So if we come to the three-dimensional problem, our computational cost will be in the solver, much more than in the stiffness matrix. Okay, let's take into account these small details if we want to go to a three-dimensional simulation.